Hey guys, we're going to go over the three problems at the bottom of the last study guide that hopefully you tried, and then you'll be assigned a few more in a Google form here that are similar. So I'm going to start by reviewing the possible four equations we have that deals with this stuff. So three of our four equations deal with velocity in them. One of them, this one, as we said the other day, is known as the wave equation. It's V equals frequency times lambda, that upside down Y symbol, that means wavelength. Um, V could also be written as wavelength divided by the time period, or if it applies, we can still use V equals little d over little t. And remember the fact that frequency equals the inverse of the time period. So I'm just going to review one of those variables individually in their units so we don't forget that. So remember, the frequency of the wave is how many cycles per second the wave goes through. All right. So how many complete cycles? Like a whole cycle would be from like a crest to crest in an image of a wave, or a trough to a trough, or any two repeating points. But remember, those were easily identifiable points. And cycles per second, another name for that unit frequency is hertz. Okay. Time period is the time it takes for just one cycle, and it's 1 seconds. Velocity is just how fast the wave is moving from one point to another. Wavelength is the distance between any two repeating points, consecutive repeating points, like a crest to a crest or a trough to a trough, and it is in meters. And if it's not in meters, we want to convert to it. And don't get little d and lambda confused because they could be both measured in meters. Little d is just a distance of travel. It is not a specific distance wavelength is. So if we just, the wave is going from some random point A to point B, and we know that distance, that's a little d. Same with the little t. The little t is not a specific time like the time period big T is. Little t is just the time it takes to get from some point A to point B. And it's also in seconds. So basically what I'm saying is just because something's in seconds, don't immediately call it a big T or a little t. You got to think a little bit of what it represents. Same with distance and wavelengths. Just something's in meters, don't assume it's a wavelength or assume it's a little d, because you got to understand which kind of characteristic is explaining. The unit itself won't 100% lock you in. All right, so let's go to these three problems. And the first of the three says Mac and Tosh are resting on the top of the water near the end of a pole when Mac creates a surface wave. The wave travels the length of the pole and back in 25 seconds. The pole is 25 meters long. Determine the speed of the wave. All right, so the first given C is 25 seconds. So that's obviously got to be a big T or little t. Now it says it's just travels the length of the pole and back. So that's not describing like anything about cycles of the wave itself. That's just a time it takes to get from point A to point B. So that makes that a little t, 25 seconds. Just a time of travel. The pole is 25 meters long. Again, that's not telling me like 25 meters between crests or troughs. That's just the length of the pole. From the wave goes from one end to the other, but it also goes it back. And they love doing this in wave problems. So it's just simple, but be careful. So while many of us might 24 meters as our little d, look right here in this sentence. It travels the length of the pole and back. So we've got to adjust this, and the d isn't just 25, it's 25 times 2, which would be a total of 50 meters. One other option could have been to keep that 25 meters, but cut this t in half, because it would take half the time to go one way. Either way, you've got to do one of those two things. You don't always have to do that. It's just something to watch out for. They really like using the fact you've got to either double something or cut something in half, like d or t, in a lot of these wave problems that just use our old equation, v equals d over t. So technically, we didn't even need any of the new equations for this problem because of the nature of it. Oh, and I just lost it. Sorry about that. I'll just put in the numbers now right here. So our new d was 50 meters divided by 25 seconds. Therefore, this wave is going 2 meters per second. All right, next one. This was pretty similar too. It says a fisherman uses a sonic ranger to determine the depth of a lake. All a sonic ranger is basically like a fancier motion sensor than what you use in class. It just sends out a wave and bounces off things to collect data, and it's able to collect information like how far it traveled and how long it traveled for. So the sound waves travel at 1,210 meters per second through the water. So that's meters per second. That's got to be a velocity. And we require 0.02 seconds to travel to the bottom and back. But look again, it says bottom and back. So 0.202 seconds is again a little t. It's just the time of travel. It's not a time period for a cycle of the wave. It's a general time of travel. But again, it's bottom and back, and we just want to know how deep the lake is. How deep would just be one way. So if we use the whole entire time, 0.02 in our formula, that's going to find a d that represents bottom and back. That's not what how deep means, right? So we got to take that and divide that by 2. It takes 0.02 seconds to go bottom and back. It would take only 0.01 seconds to go half of that. And that's what we're being asked. So we want to find d, and of course we'll use again this little equation, solve it for d, do the basic algebra correctly, and we got 1,210 times 0.01 seconds, and multiplying those two things will give us 12.1 meters. So again, hopefully simple as long as you understand the basics of stuff. And finally, the last question, it gives us a diagram on your actual sheet. I drew a similar diagram here. Not as good as that one, but it'll do. So it says the waterways below are traveling with a speed of 3 meters per second and splashing periodically against Wilbert's perch. That red block represents the perch from the original picture. So right now it's already in the diagram, but meters per second. Each adjacent crest, now if you're not familiar with the term adjacent, it means side by side. So each side-by-side crest is 6 meters apart, as shown in the diagram. And what we need to realize right away is that it's really telling us that wavelength, because that is a more specific value in meters. It's not just some distance of travel right now, that's meters. It's telling me it's a distance between adjacent crests or back-to-back, side-by-side crests. So that is a wavelength, that symbol that looks like an upside down Y, lambda. How much time passes between each successive drenching? Now, again, this is not asking for a little t just because it says time. It says how much time is passing between successive drenchings. So that would be really asking me how long does it take to complete a cycle of the wave, successive drenchings, if he gets drenched every time a crest basically comes up, the perch right there, right? So I want to find a big T, And it says answer explained using complete sentences or a calculation. Well, it's the easiest to do with a calculation. So looking at what we got, we look at our formulas, and we got V equals lambda over T is one of our formulas that fits there. And we do have to solve that for the big T. So doing our algebra correctly will be T equals, basically flip the V and the T. That'll be lambda over V. So that's going to be 6 meters divided by 3 meters per second. And that will give me a time period of 2 seconds. So basically, if we look back at the diagram, Wilbert on this perch right here is going to get splashed every 2 seconds, because every 2 seconds a cycle will reach there, and it will go through a full cycle and get there from the one crest to the next, as long as we're assuming this wave stays consistent, which we are supposed to assume.